In this video, I'm going to talk about how to think about the gravitational potential energy stored by a planet and an object orbiting it, and how we can actually calculate the gravitational potential energy of the system, and how to think through how the gravitational potential energy changes of that system, and then therefore the kinetic energy also changes. At this point, we've only talked about gravitational potential energy in the context of a planet and another object with mass. We say that the Earth and the object system together store gravitational potential energy when those objects are separated. So if a skydiver is above the surface of the Earth at some height y, we can calculate the gravitational potential energy stored by the Earth skydiver system by taking the skydiver's mass times the planet's gravitational field strength times the distance they're separated from wherever we define a height of 0. And this only works if the gravitational field strength that we're talking about is constant, and at least near the Earth's surface or near a planet's surface, it's relatively constant. So if we were to graph how the gravitational potential energy changes as an object's height gets higher and these two things are separated further, as long as the gravitational field strength stays the same or is relatively constant, the gravitational potential energy will increase linearly with height. Well, that doesn't quite work anymore when we talk about, let's say, the moon orbiting the Earth or a satellite orbiting the Earth, because the farther you get away from the Earth's surface or the center of its mass, the weaker the gravitational field strength is. If we use Newton's universal law of gravitation, we'd actually come up with an expression, and we have in class already, for the gravitational field strength at any distance away from the Earth's center. It's the universal gravitation constant, big G, times the mass of the Earth or the mass of any planet divided by that separation distance squared. And that separation distance, remember, is from the center of one mass to the center of whatever other mass we're talking about. So as that distance is much bigger than the Earth's radius, then G is much smaller than about 10 newtons per kilogram or 9.8 newtons per kilogram. So if we were to try to make a graph of how the gravitational potential energy of, let's say, the Moon-Earth system changes as we move that moon or that object farther and farther away from the Earth, it would start out linear, but as you get further, the amount of gravitational potential energy increase that you'd have by the system with increasing distance would become less and less. Because remember, where does this gravitational potential energy come from? If you're physically moving the moon or you're physically moving an object, separating it from the planet it's next to that it's being attracted to, you have to do work to move it to a farther distance. You have to do positive work. And the farther you bring it from that planet, the less work you have to do because you don't have to overcome as large of a force because the gravitational attraction gets weaker and weaker and weaker. So if we were to graph the gravitational potential energy of a planet orbiting object system, as radius increases, as the separation distance increases, this is how the gravitational potential energy would change. To come up with that equation, you can use calculus to derive that answer. For us in AP Physics 1, it's algebra-based. You're just going to be given this equation. The amount of gravitational potential energy stored by a planet and another object is equal to negative G, that's the universal gravitation constant, times the mass of the planet, times the mass of the other thing, divided by the separation distance squared from the middle of one to the middle of the other. On your AP Physics 1 equation sheet, it just looks like this. UG equals negative G, big G, times M1 times M2 divided by R. So this gives us actually the gravitational potential energy stored by any two mass system when they're actually separated. But this might seem a little strange. Whenever we talk about energy, we've always said that you have zero energy and positive energy. Why does this include a negative sign? Well, it has to do with where you define a height of 0. We've always defined a height of 0 or a vertical position of 0, the lowest an object can possibly get, so we don't have to talk about negative gravitational potential energies. But we could define a height of 0, let's say at the highest an object gets. If the skydiver is up here and we're saying it's at a height of 0, we'd say they have 0 gravitational potential energy stored because they're at a height of 0. Well, what would that mean about the gravitational potential energy down here? Well, if we define a height of 0 up here, they're actually at a negative vertical position. They'd store negative gravitational potential energy. And in the context of the problems we've already solved, it usually doesn't make sense to talk about it like that. But when we talk about planet and orbiting object systems, it actually makes sense to change our definition of where we say there's 0 gravitational potential energy. So coming back to this situation, if we were to define a height of 0 up here, at a higher height based on this graph, if this is where a height of 0 is, then this is how our gravitational potential energy would change as a function of vertical position. The lowest it gets, it has a lot of negative gravitational potential energy, and the higher it gets, it has less negative gravitational potential energy until it gets to our highest height of 0. Let's think about how this applies to the situation on the right. If we have a planet and another object system, let's say they store 0 gravitational potential energy, not when they're touching or not when their masses are as close as possible, but when their masses are as far as possible. Let's say the separation distance is at an infinite distance away. So we'd say there's 0 gravitational potential energy when the r is infinite. So if we take this shape and we kind of transfer it over here, we'd see that when two objects are close, they have some kind of negative gravitational potential energy. And as r increases, they have less negative gravitational potential energy. And eventually, once they're an infinite distance away, essentially there'd be 0 gravitational potential energy. I know this is definitely different in the way that we think about gravitational potential energy, but it's helpful when we talk about orbiting object systems and finding something like the escape velocity, which we'll do at the end of this video. So let's just think about how this applies to an elliptical orbit of a moon around a planet. If it's in an elliptical orbit, sometimes it's closer, sometimes it's farther away. And we've already talked about before that when it's closer and there's less gravitational potential energy, the system has more kinetic energy, so it's moving faster. And when the object is farther away from the planet and it has more gravitational potential energy, the magnitude of it is greater, then it's going to be moving slower because there's less kinetic energy. So sometimes you're asked to find either the quantity of how much the kinetic energy changes from one position to the other, or how much its gravitational potential energy changes. Well, let's use our new equation to calculate or think about the gravitational potential energy stored at any distance to help us get an expression for that. So let's first think about some energy bar graphs, which now look a little bit different because now we can have negative energies. It's not just 0 or positive. So when it's at position A and it's the closest, it's moving fastest. So it's got a lot of kinetic energy in the beginning. And when it's at position B, it's farther away, it's moving slower. So let's say it starts out with 4 bars of energy and now it only has 3 bars of energy. So what do we do with the gravitational potential energy? Let's finish our energy bar graph. Well, when it's close at position A, that means it's a small radius, and the smaller radius you have, the larger amount of negative gravitational potential energy you have. So let's just say at position A, there's 3 bars of negative gravitational potential energy. Well, what about position B? It's at a larger separation distance, so r is bigger here, and if r is bigger, you're dividing by a larger denominator, so that means you're going to have a smaller negative gravitational potential energy. So over here for position B, let's just say there's now only 2 bars of negative gravitational potential energy. And here we're assuming it's a closed system. The system is just a planet and the moon. There's nothing outside the system applying a force to it, so there's no work being done. So the total amount of energy we start with has to equal the total amount of energy we end up with. Energy is conserved. There's no work being done. There's no energy transferred into the system or out of the system. It's just rearranged. So let's write down our energy conservation equation. So we have the kinetic energy plus the gravitational potential energy at position A must be equal to the kinetic energy plus the gravitational potential energy at position B. If we wanted to find out what the change in kinetic energy is, not the kinetic energy at a specific position or the change in gravitational potential energy, let's rearrange this and solve for the change in kinetic energy and the change in gravitational potential energy. So I'm going to leave UGA on this side, and I'm going to subtract UGB from both sides, effectively moving it over to the left side. And then we're going to leave the kinetic energy at position B on the right side and subtract Ka from both sides, effectively moving it over to the right side. So we get that the gravitational potential energy at A minus the gravitational potential energy at B is equal to the kinetic energy at B minus the kinetic energy at A. And whenever we're subtracting two values from one another, you get essentially the change in that value. So we can see that the magnitude of the change in the gravitational potential energy when it goes from A to B has to be the same as the magnitude of the change in the kinetic energy that it goes through from A to B. And if we look up at our energy bar chart, let's see if that actually makes sense. Does the change in gravitational potential energy equal the amount of change in kinetic energy? Well, the kinetic energy went down by 1 bar, so therefore the gravitational potential energy has to go up by 1 bar. But it was -3 bars. So how do you go up by 1 bar? You go from -3 bars to just -2 bars. So you can see that the amount the kinetic energy changed has to be equal to the amount the gravitational potential energy changes. So if we want to get either a quantitative answer or a symbolic expression for either the change in gravitational potential energy of the system or the change in kinetic energy of the system, we can use this new equation to come up with that. So let's say we wanted to figure out how much the kinetic energy changed, and we didn't know what the velocities were at A and B. We weren't allowed to use those expressions. We were just allowed to use distances, let's say RA and RB. So the change in gravitational potential energy from A to B would be the final energy minus the initial energy. So if we're going from A to B, the final energy is at position B, the initial energy is at position A. So we'd find the gravitational potential energy at position B, or the separation distance B, minus the gravitational potential energy at position A. And the gravitational potential energy is given by this equation. So we have -g times the two masses, the mass of the planet times the mass of the moon, big M times little m, divided by their separation distance, and at position B it's RB, minus the gravitational potential energy at position A. It's -g times the mass of the planet times the mass of the moon divided by that new separation distance. So both terms have big G, big M, and little m in common, so let's factor that out and see what we have left over. So if we factor that out, we get big G times big M times little m, and what's left over is -1 over RB. We have minus a minus, so that turns into plus 1 over RA. So this expression right here represents the difference in gravitational potential energy from A to B, and that's the same as the amount of change of kinetic energy as we showed up here. So let's see how we can use this concept to figure out something called the escape velocity, which is essentially how fast an object would have to be traveling so that, let's say if you launch this object at that velocity and it had no means of propulsion, that essentially would keep going farther and farther and farther and farther away from the planet, never to actually return. If it wasn't moving at least at this velocity, the gravitational attraction would slow it down and then eventually it would speed it back up. If you're moving fast enough, you can actually escape the gravitational confines of a planet and you never actually return. That's what's meant by the escape velocity. Well, before we get there, let's just think about, let's say we have a rocket and it's going at some really fast velocity near a planet of big mass M, and the rocket has little mass M. And let's just say it reaches some distance where it's effectively an infinite distance away. It's light years and light years and light years away. The gravitational attraction on the rocket from the planet is so negligibly small where we would define there's essentially zero gravitational potential energy between the rocket and the planet. When we look at our energy conservation equation and our energy bar chart, it might look like something like this, where let's say it starts with some amount of kinetic energy, it's got 3 bars of negative gravitational potential energy. Let's say all the way at this near infinite distance where the gravitational attraction is negligible, there's no gravitational potential energy stored. So there would be no negative bars of gravitational potential energy. And let's say it still has a velocity. So it's got some kinetic energy. And we could figure out, based on how fast it's moving initially and how much negative gravitational potential energy it has, we could figure out how fast it would be going at this really far distance. Well, if we go a little bit slower than this initial velocity, then the escape velocity is essentially defined as the velocity you need to have so that when you're just coasting and gravity's slowing you down, by the time you make it to this near infinite distance, you'll have no velocity left over. That's the minimum velocity you need to escape the gravitational confines of a planet. So if we're going to find an expression that would allow us to solve for the escape velocity around any planet, let's first see how that's going to modify our energy bar chart and our energy conservation equation. So if this escape velocity is a little bit smaller than what we were assuming over here, let's take a bar off of here. So let's just say this thing starts with 3 bars of positive kinetic energy and 3 bars of negative gravitational potential energy. So we're assuming that in the end, there's no velocity, so therefore there can't be any kinetic energy, and it's not going to show up in our energy conservation equation. So to solve for the escape velocity, you basically have the initial kinetic energy plus the initial gravitational potential energy equals 0. So if we just plug in our equations that we know for kinetic energy and gravitational potential energy, we can find an expression to solve for that escape velocity. So kinetic energy is just equal to 1/2 mv squared. So it's 1/2 times the mass of the object that's trying to escape the planet times its escape velocity squared. Then we're adding to that the gravitational potential energy that exists at that initial position, which is going to be negative g times the mass of the planet times the mass of the rocket divided by their separation distance squared. In this case, we've got the rocket already starting away from the planet, but if the rocket was on the planet's surface, this separation distance would just be the radius of that planet or that moon or whatever type of gravitational object you're trying to escape. So we set this equal to 0. So let's just add this term to both sides, effectively moving it over to the right side. So we get 1/2 mv squared equals big G times the mass of the planet times the mass of the rocket divided by the initial separation distance. And notice there's a little m, the mass of the rocket, on both sides. So let's divide by little m, cancels it out. We get 1/2 v squared equals big G times big M over R. So a couple steps of algebra, we just multiply each side by 2. It effectively moves a 2 up here in the numerator. Then we get the escape velocity squared is equal to 2gm over R. So let's just take the square root of everything. So we get that to find the escape velocity needed to leave a planet, let's say if you're standing at the radius of the planet, is just the square root of 2 times the universal gravitation constant times the planet's mass divided by the planet's radius. I hope this has been helpful in grasping how to think about gravitational potential energy in orbiting systems and to think through changes in gravitational potential energy, changes in kinetic energy, and even finding the escape velocity for a planet.